We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, the dumper truck. How do you make a machine that can move mountains? Light bulbs. What connects bamboo and pencil lead to the discovery of the incandescent bulb? The piano. Tickling the ivories or hammering the strings, we explain the complex engineering behind this musical marvel. We reveal the surprising science and amazing manufacture behind these wicked inventions. Dump trucks are a vital tool in the construction industry today, with their ability to carry huge amounts of building waste and rubble, automatically tip their trailer, and of course, dump the rubble fast. But where did it all begin? Predecessors of the dump truck could be found on the farms of Western Europe in the 19th century.
A lot of British and German manufacturers saw there was a demand within farms, within kind of low-level rural production industry to have the capability to load something into a truck and be able to tip it out.
Two-wheeled, horse-drawn box carts were used that could tip their rear once unattached, saving farmers from carrying heavy loads. With the use of the internal combustion engine in motor vehicles in the late 19th and early 20th centuries, it wasn't long before these new vehicles were adapted to be able to transport cargo. The original flatbed trucks were adapted to have a design that allowed them to tip, although early versions of these tipping trailers were operated manually with a rope and pulley system, and new designs were created that automated the tipping process. In 1904, the manned gravity dump was released. This, as the name suggests, used gravity to allow the trailer to tip automatically. This was achieved fairly easily by simply adjusting the position of the trailer bed, therefore changing its centre of gravity, meaning that it would tip when attached from the motor that pulled it. However, it wasn't until hydraulic dump beds were introduced in around 1910 that the dump truck of today really began to take shape.
Around the 19th century, you start to see companies like Freuhoff develop hydraulic trucks, which would be a flatbed, which usually through a process of gas hydraulics would be able to then raise and distribute their goods evenly.
Demand for these trucks would increase dramatically as World War I began, and they would aid with wartime demands, such as the removal of soil and rubble in trench digging, as well as carrying much-needed supplies. Post-war, with these new dumper trucks being recognised for their versatility, sales skyrocketed in the 1920s, ensuring that they became a necessity in small and large-scale construction work. Today, hydraulic systems are still used in dump trucks, much like the early models. With improvements made to the engines and chassis being made throughout the 20th century, these dumper trucks can be absolute behemoths, capable of lifting a huge 23 tons in weight. That's 3 elephants worth of weight all in the back of one truck. So, we know what they can carry, but how are these dump trucks made? Terex Trucks produce dump trucks from their factory in Scotland. But what does the power of nearly 300 heavyweight boxes have to do with their production?
Here at Terex Trucks, we design, manufacture, sell and support 2 types of off-highway truck. We go from what we call the baby, which is a 30-ton capacity articulated truck, all the way through to a 100-ton capacity rigid truck. So at Terex Trucks, we are what we would describe as a vertically integrated factory. And what does that mean? It means that we design the product from a blank sheet of paper. We then start to procure the materials from raw steel, raw materials, and we literally cut the metal, bend the metal and machine it, weld it together, and then we build the frames, the bodies, and ultimately we then assemble the whole truck.
The manufacturing of one of their huge dump trucks begins with ginormous steel sheets. These sheets are cut to shape using plasma and gas burners. Each cut piece will fit together, almost like a jigsaw, to form the truck.
And each sheet of metal that we bring in, we try to utilise 85% of that surface area to reduce our waste. So yes, we cut with plasma and gas into the shapes, what I call the first jigsaw puzzle pieces that eventually, as we move through the processes, become chassis, become parts of the axle, become parts of the support mechanism for the truck. So that's the first stage, and we call that processing.
The plasma burners are capable of cutting steel of between 6mm and 20mm in width, whereas the gas burners can cut up to 150mm using the intense heat they produce. These cut sheets are then moved onto a machine called the press brake. Here, a whopping 1,000 tons of pressure is literally pressed down onto the steel sheets to shape them. That's the power of 286 heavyweight boxes all throwing one big punch at once. When bending the steel, accuracy is vital, as each separate piece has to fit together exactly to form the truck. The shaped steel will go on to form the frames and the bodies of the dump trucks. Now that our steel is cut and shaped, it is welded together. Because of the heavy-duty work that these trucks will endure, these welds have to be extremely strong and fault-free. The welds are checked constantly by the trained eye of the engineers, as well as being ultrasonically inspected, ensuring that no weak welds slip through the net. From here, the bodies and frames are shot blasted. Shot blasting removes any imperfections in the metal in preparation for painting. Once shot blasted, the metal must be painted in under 4 hours to prevent any oxidation of the metal that could cause rust or instability. Freshly painted, the frame and body are now ready to be moved onto the assembly line. While all this was going on, the sub-assembly parts of the truck have all been machined in Terex's state-of-the-art machine shop. These include front and rear axles and differentials, all ready to be assembled with the freshly welded and painted frame. The front axle is assembled first, then the engine and transmissions. The all-important hydraulics, tanks and platforms that make this truck a dump truck are then assembled, before the brake packs and rear axles are fitted. The assembly line is capable of producing an articulated truck every 185 minutes. That's 5 every day. The bigger, rigid trucks take a little longer, but the factory are still able to produce 2 a day, keeping the world well stocked with dump trucks. Once off the assembly line, the trucks are thoroughly inspected and tested to raise and fix any issues and imperfections. A total of 6 hours on the test track are needed, meaning that every truck that leaves the factory is in faultless working order and able to be put through even the toughest of requirements. When all of the tests have been passed, the trucks are washed and delivered worldwide, ready to assist the mining, waste, building and many other industries.
So these trucks go to work in gold mines in Africa, diamond mines in Russia, and coal mines in China, Indonesia, Australia, and all across the world, including the Americas.
From a simple horse and cart to these great monsters, the dump truck truly is a wicked invention. Today, we might take them for granted, but with a flick of a switch, this technology illuminates our world, allowing us to work once night has fallen and transforming the view of the Earth from space. The light bulb has indeed transformed our homes and how we live, and we can't seem to do without them. It has been estimated that there are around 12 billion light bulbs glowing in the world right now, with over 5 million sold every day in the US alone. The question of who actually invented the light bulb is a great deal murkier than the bulb itself, with some historians claiming up to 22 different inventors had types of incandescent light bulbs working before the bulb was made famous by the American inventor Thomas Edison in 1878. Indeed, British scientist Humphrey Davy had a working bulb in 1802, and as Edison worked hard on his design 70 years later, another Brit, Joseph Swan, was also busy fitting his bulbs to English houses. While others experimented with creating bulbs of expensive and brittle materials, Edison struck on a design which turned the light bulb into a commercial success.
He submitted the patents and didn't work out until a lot later, about 7 months later, that carbonized bamboo worked as a very, very good filament. What this means is you can heat it up, it can produce a glow, it can light and it can last for 1200 hours. That's a good effort for an early light bulb, and was essentially key to making it a commercial success, because it can be made quite cheaply. Bamboo is a relatively cheap source material. Carbonizing it is just burning it in the presence of not too much oxygen, and then putting it inside the light bulb at one point, it'll work.
Some of these early light bulbs are still working today, with the record held by the Centennial Light in California, which has been glowing since 1901. Unlike that old-timer, typically an incandescent bulb will last for about 1,000 hours. So, how does a light bulb actually glow?
A light bulb works by having something getting very hot, and when it's hot, the electrons in the whatever the filament is, the electrons move up an energy level or two. The energy levels exist, but they're not normally used until they're excited. Electricity passing through carbon, passing through tungsten, moves the electrons up a couple energy levels. As these electrons then restore themselves back to what the normal electron level is, then at that point, they give off light.
Another important part of Edison's design was successfully creating a vacuum inside his bulb. When air touches a light bulb's filament at high temperatures, the filament oxidizes, becoming weak at points which can lead to a break and no light. The vacuum inside a light bulb acts to prolong the life of the light bulb's filament by keeping it from oxidizing too quickly, and stops the bulb from being blackened by the results of this reaction. In the early 1900s, inert gases, which are gases that do not react easily, such as argon and nitrogen, were put into the bulbs, which reduced the reaction even more, so no more blackened bulbs. The carbon filament was also replaced by metal tungsten ones, which can easily cope with the 2000 to 2500 degrees Celsius temperatures the filament reaches when switched on. These type of bulbs are the ones that we have been using for the last 50 years or so. But they come with one major limitation. They are terribly inefficient. Only 2.5% to 5% of the energy used by your average bulb is actually converted into light, with the rest wasted as heat, and it has been estimated that 1/4 of all home electricity consumed is used to power them. The answer was fluorescent lamps. Basic fluorescent lamps had been developed at the same time as their incandescent cousins in the late 1800s. But it wasn't until their commercial potential was realised in the 1930s and the subsequent demands for cheap lighting in the wartime factories of World War II that they started to take off.
What happens is you have ionised mercury vapour, and an electrical discharge is put through the system, which is why they take a bit of time to turn on and flicker a bit often, and then warm up. The reason we use mercury is this. When an electrical discharge goes through it, instead of producing visible light, it produces lots and lots of UV light. UV light hits the phosphor then absorbs the energy, and an electron goes up an energy level or two, and then it drops down, and in dropping down the energy levels, that process gives off light. The benefit of this is, because we're generating ultraviolet light with a very small amount of material, we're generating less heat, and we're converting most of the energy much more efficiently into visible light.
Today, smaller versions of the big fluorescent tubes have made it into our homes in an order to create more efficient lighting. Only giving off 25% the heat and lasting 10 times the life of a conventional bulb, compact fluorescent lamps, or CFLs, create light in the same way as their larger and more established cousins, and these are now driving forward the movement towards more energy-efficient lighting. The light bulb, truly a wicked invention. Can we create our own DIY light bulb by just using a pencil lead? We're going to need 6 D-cell batteries, electrical tape, 2 wires with alligator clips, a pencil lead, a jam jar, and a matchbox tray. For this wicked challenge, we're going to need some serious power, so we connect all the batteries together. Our pencil lead filament is connected to the wires with croc clips, and the jam jar is placed over the top. We're ready to go. We connect the wires to the mega battery, and the pencil lead starts to smoke and then glows like an incandescent bulb. Electrical current is actually the flow of electrons through a material. Good electrical conductors like metal and our pencil graphite are comprised of atoms surrounded by electrons, with additional electrons that are free to move around the object, and this allows the current to flow easier. Depending on a material's properties, size, and the amount of current that it is subjected to can create conditions where the electrons keep bumping into the atoms as they travel through the material. This is known as resistance. The collisions transfer kinetic energy to the atoms, which in turn heat up, and this generates light. And the jam jar? Using the jar limits the amount of oxygen present around the burning graphite, slowing down the reaction, meaning the lead will last longer and not break under the strain. So, can we create our own DIY light bulb by just using a pencil lead? Yes, we can. Wicked challenge, smashed. Pianos have been with us for centuries, but do you know just how far back their history goes, and that their history draws a link between Iraq and Italy? Open up a piano and you will see that it is much more than just keys making a sound. The piano is an engineering marvel, with complex mechanics all working together to strike strings with hammers in order to make beautiful music.
So it might be surprising to learn that pianos actually come from the same family of instruments as guitars and violins, which are called chordophones, and they use the concept of having a string held at pressure between two different points. And chordophones have been around for thousands of years, but the modern piano, as we know it, has been around in its current form since roughly the early 18th century.
The lyres of Ur, located in what we now know today as Iraq, are considered to be the world's oldest surviving stringed instruments. The pieces found date back to 2,500 BC, over 4,000 years ago. Stringed instruments that stemmed from these ancient lyres took on many shapes and sizes and were played in many different ways, but it wasn't until the 14th century that a keyboard was used. The harpsichord was a vital step towards inventing the piano. Its ability to project sound more loudly than its predecessors and refinements in the action, which is the mechanics that turn key presses to string hits, inspired many more musicians to turn to playing keys. In the very early 16th century, a famous harpsichord maker named Bartolomeo Cristofori invented a new instrument in Florence, Italy. First exhibited in 1709, Cristofori's new instrument was named un cembalo di pianoforte, which translates roughly to soft and loud keyboard. The name was eventually shortened to, you've guessed it, piano. This piano offered musicians the chance to control volume with their key presses, giving much more scope for compositions. This piano is very similar to those used today, with a few tweaks and changes such as the addition of pedals. It's amazing to see just how similar the modern piano is to Cristofori's invention.
So the 88 keys that you see on a piano are made up of 52 white keys and 36 black keys. Now when you press down on these keys, a hammer strikes down on the string, which creates the sound. And then when you release the key, a damper stops the vibration and stops the sound from happening. But you can keep the sound going, you can sustain it using the pedals.
But just how are they actually made? The making of a piano is a highly skilled process that requires extreme care and attention to detail. Cavendish Pianos in England's Yorkshire Dales are the last remaining piano manufacturer in Britain. A piano's life begins with the construction of the soundboard. The soundboard is essentially an acoustic amplifier, not too dissimilar to a drumskin.
If I was to take a piano hammer and a piece of wire under tension and to hit it, you'd hardly hear any sound at all, and there'd be no character to that sound. It'd be a very, very small sound. Yet, by making a soundboard, we can change that sound from being something that you can hardly hear to being a sound that can fill a whole concert hall with sound.
The board is made of tone wood that has been meticulously selected. Only 3% of this wood makes the grade to be used in a piano. This board is placed onto a curved frame. This arc, almost invisible to the naked eye, would form a huge spherical shape if it was continuous. This curve is vital in giving the soundboard the correct tone and amplification.
The curve is essential. Now that radius that's put on the soundboard means there is always tension there. There's always tension in that piece of wood. It's always sort of struggling, and that's what produces a sound.
Wooden ribs that have been tuned by in-house craftsmen are placed and glued onto the board. These ribs are then clamped into place using wooden poles called go bars. that force immense pressure onto the ribs and soundboard, forcing it into the curved shape of the frame. Once the go bars are in place, the whole structure resembles an extremely well-crafted mini forest. The whole process is undertaken in a climate-controlled environment of precisely the right humidity to ensure the wood is at its prime. Once the glue has dried overnight and the go bars have been removed, a bridge is glued onto the other side of the soundboard and fixed into shape, again using the go bars. The soundboard is now complete and can be glued onto the back posts of the piano. The cast steel frame is then lowered into place onto the structure and fixed into position. It is now time for the stringing of the piano. This time-consuming process sees every string of the piano fixed into place. Here, the bass strings that will give the low notes are being fixed into position. The metal strings are threaded and wound onto pins before being secured into the piano with a hammer. Once the strings are in place and the boards have been left to rest overnight, in order for all the tensions to be eased and stabilised, the fixed case parts are added to the piano. These case parts are carved and produced by local suppliers, ready to be fitted. Here, the sides of the piano are glued and fixed into place. The key bed is then attached, ready for the keys. Once all of the case parts have been fitted, it is time to install the piano's action. The action mechanism is the mechanical assembly which translates the depression of the piano keys into the rapid motion of the hammer, which creates sound by striking the strings.
And there's a lot going on between the tip of finger and the string. All the wooden parts of the action mechanism which all have to be regulated perfectly so that a piano is not just sounding good but feeling good for a professional musician who has very high expectations and needs a piano to do exactly what he or she wants.
The construction of the action takes a whopping 20 hours due to its complicated structure and a need for faultless production. Dampers are then glued into place and lined up precisely with the piano strings. After the keyboard has been installed, the piano is tuned and then bashed in a piano crusher. This piano crusher quite literally bashes all of the keys at once, playing every possible note several thousand times. The rest of the detachable case parts are then added before the piano is tuned one last time. Once the piano tuner is completely happy that every note is pitch perfect, it is time for music to be made.
You're doing something really rather special in that you're getting together some bits of metal, some bits of wool, felt, and some bits of wood, and you're making a machine that sings, essentially. So it's a kind of alchemy of taking these ingredients, these sort of inert ingredients, and making an actual living thing.
The piano, truly a wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. The dumper truck, light bulbs, and the piano. All wicked inventions.